Okay, today we are doing the convergence review problems on page 748 of the textbook for infinite series. So starting off with number 3, which is an infinite series starting from 1 and going to infinity of 1 over n squared plus n. Now this one is not too tricky. We can notice at the bottom that the n squared plus n for when n is positive, which we know it always will be positive since it starts at 1, will be less than n squared, or will be greater than n squared. N squared, which means, because it's in the bottom of the fraction, that 1 over n squared plus n will be less than 1 over n squared. And this is a p-series where p equals 2, which means this converges, so therefore, since this is less than that, for all values of n, this series also converges. So, convergence. That was pretty simple. Now we'll go on to number 6, which is the series from n to infinity of 3n over 1 plus 8n to the n. So the first thing I notice in this problem is that we're raising everything inside to the nth power. So there's a few ways to do this, or I guess there's 2 ways that come to mind. There's the root test, and there's also a geometric series. So the root test, we didn't go over much in class, so I'm going to be doing away with the geometric series, and I guess this is also a direct comparison test. So 3n over 1 plus 8 to the n, just looking at the inside the parentheses part right now, this, we know since n is always positive, we know this will be less than 3n over 8n, right? Because this is greater than this, and this equals 3/8. So that means we know that 3n over 1 plus 8n is always less than 3/8, which means that this is always less than this, which is a geometric series. Where r equals 3/8. And since the 3/8 is less than 1, we know that this converges, so therefore, because this is less, this also converges. So this converges. Like so. Oh, wait. K squared times e to negative k, which that is just k squared over e to the k. And so what I'm going to do for this one is a ratio test. So I'll take the limit as k approaches infinity of the absolute value of, it'll be this, what the series is, of k plus 1. So k plus 1 squared over e to the k plus 1, and then divide that by just the normal function itself. And then I'm just going to rewrite this so it's a bit easier to look at and to follow by multiplying by the reciprocal. So it looks like this. And then from here, we can see that since this e to the k plus 1 is really just e to the k times e to the 1, the e to the k part will cancel with this e to the k, and we're just left with e on the bottom, so, or e to the 1 on the bottom. So that equals the limit as k approaches infinity, the absolute value of k plus 1 squared over e times k squared. Now, intuitively, we can see that as k approaches infinity, as k gets extremely large, the k plus 1 squared and the k squared are practically the same value, so they'll just cancel out, and we will be left with 1 over e. But if you want a more mathematical sort of justification for this, we can see that if we expand out the k plus 1 squared into k squared plus 2k plus 1 squared, or 1, over the denominator, we can then multiply both sides, or multiply the top and the bottom by 1 over k, which is essentially just, or 1 over k squared, I mean, which is essentially just multiplying by 1, so the value doesn't change, but we can rewrite this as, so k squared over k squared over k squared is 1, plus 2k over k squared, or just 2 over k plus 1 over k squared, divided by e, because the k squareds cancel out. So then, since we are taking the limit as k approaches infinity, the 2 over k and the 1 over k squared, these just become 0. So again, we are left with 1 over e, and this is less than 1, so therefore this converges. Right, that was number 9. Now moving on to number 12, which is the sum from n equals 1 to infinity of of negative 1 to the n times n over n squared plus 25. So this one, immediately, what comes to my attention is the negative 1 to the n, which means this is an alternating series where the terms alternate between negative and positive. So all we need to see for an alternating series is whether this part, the other part, the non-negative 1 part, if the limit as this approaches infinity converges to or goes to 0. So the limit as n approaches infinity of n over n squared plus 25, and we can see that because the n squared, there's a greater power of n on the bottom, that this will in fact go to 0. But again, if you want a more mathematical justification, we can again multiply by 1 over n times, or over 1 over n, which again is just 1. And we see that the top equals 1. Limit as n approaches infinity of n over n, or 1, over n plus 25 over n. This just goes to 0, and we're left with the limit as n approaches infinity of 1 over n, which is 0. So this goes to 0, therefore this series is convergent or converges. So that one is pretty simple. Moving on to number 13, which, let me just find it really quick. Okay. Three to the n times n squared over n factorial. So when I see the factorial, that immediately tells me that I should use the ratio test. So I will again take the limit as n approaches infinity of the top, or of this whole thing, but n plus 1. So n plus 1 there. And what this essentially, oh wait, my bad. What this essentially means is that the n plus 1 is the next term, and we're dividing it by this thing itself, absolute value. So basically, since we're taking the limit as n approaches infinity, if this is greater than 1, then the top section, this part, is greater than this part, which means each subsequent term, because this is n plus 1, right? So each subsequent term is actually getting bigger, and therefore the series will not converge. But if the output of this limit is less than 1, that means the top is less than the bottom. Each subsequent term is getting smaller. So that means the function will converge. And then if it equals 1, then this test is inconclusive. So since this is homework problems, we won't get a 1, but that is what happens. So, okay, I'm gonna get rid of this. Now I'll rewrite this to make it in a form we're a bit more familiar with. So again, like last time, just multiplying by the reciprocal. So n factorial over 3 to n times n squared. And then again, we can cancel out the 3n and 3n. And with factorials, what you can do is n factorial equals n times n minus 1 times n minus 2, etc. And n plus 1 factorial equals, I'll do parentheses to make this a bit more clear, n plus 1 times n minus 1 times n minus 2, etc. So these are all the same terms, right? This corresponds with this corresponds with this corresponds with that. So we can see that if we're dividing these, this will cancel, that will cancel, and that will cancel with the respective terms on the bottom, and we're left with just n plus 1. So we can rewrite this as 3 times n plus 1 squared over n plus 1. Cool. And now, or times n squared. And now this cancels with that. And since the n squared is on the bottom, that means that this and the n squared is and the n is on the top. So the power on the bottom is greater than the power on top. that means this limit equals 0. And that means actually that not only is this convergent, but it's absolutely convergent. So we can mess with this with the ends. We can make n negative, or we can make it alternating or whatever. But regardless of what we do, it will still converge, which is why it's absolutely convergent. And that only happens, well, in the case of the ratio test, that happens when the limit equals 0. So I'll go to the next problem, which is problem 18. The sum from n equals 2 to infinity of -1 to the n minus 1 over radical n minus 1. So again, this section, the -1 to the n minus 1, tells me that this is an alternating series. So we'll just take the limit as n approaches infinity of the rest of the expression, 1 over n, or 1 over rad n minus 1. And this, I mean, it's pretty obvious, as n gets bigger, this equals 0. So this is convergent. Oh, whoops. Convergence. Okay. That one is pretty simple. Now problem 21, which is this one is I'll just write it down first. -2 to the 2n over n to the n. Now for this one, what can we do? This one, I guess there's a few things to do. First off, I'll just factor out I'll take out the n in the exponent and make this -2 over n -2 squared to the n, or -2 squared over n all to the n. And so -2 squared equals 4. So that means this can be rewritten 4 over n to the n. And so now we can do the root test. Yeah, I guess we would just do the root test. So we'll just take the nth root of this expression. So the limit as n approaches infinity of the nth root of 4 over n to the n. And now the n, this cancels out. We're left with the limit as n approaches infinity of 4 over n, which equals 0. So this is also convergent. And actually is absolutely convergent. All right. Now moving on to 24. Is the expression is cosine of n over 2 over n squared plus 4n. So this one I can see, just looking at the numerator, that cosine of n over 2 is always less than or equal to 1 because the range of the cosine function is -1 to 1. And then I can also see that n squared, because n is always positive, in this case, n squared plus 4n is always greater than n squared. So since the numerator is also always less than 1, the denominator is always greater than n squared, we can see that this whole thing is greater than, or no, is less than 1 over n squared. And this again is a p-series where p equals 2, and therefore this converges, so this converges as well. Okay. Oh, I've reached the bottom of the thing. With a little notepad, hopefully it'll let me go farther down. So 28 is e to the 1 over n over n squared. Now, this one, I guess, is a little trickier, but what we can do actually is an integral test, because if we think about it, the function, well, first off, it's continuous, right? Except at n equals 0, but since this starts at n equals 1, we don't have to worry about that. And also, it's always decreasing, which we can see because the numerator, as n increases, is always getting bigger, and the denominator, sorry, as n increases, is always getting bigger, and the numerator, as n increases, because this is e to the 1 over n, is always getting smaller. So with those two things, we know that this decreases as n increases, so we can do the integral test. We're going from n equals 1 to infinity, so those will be our bounds. So the integral from 1 to infinity of e to the 1 over n squared dn. Now this is an improper integral, which means we will rewrite it like so. The limit, as we can do any variable. I'll just pick t. The limit is t approaches infinity of the integral from 1 to t of e to the 1 over n squared dn. And now, let's see, I guess I will use up. So u equals 1 over n, which means du over dn equals, wait, let me think. Yeah, -1 over n squared. So that means that dn equals, here, I guess I'll just write it down. You can obviously just do this mentally, but dn equals negative n squared du. So we can replace this as, oh man, this is long. The limit as t approaches infinity of the integral of 1 to t of e to the u over n squared times negative n squared du. And so this cancels with that. We'll take the negative and take it outside of the integral. And then we're pretty much just left with e to the u, which is just e to the u, right, when we anti-differentiate it. So that's negative. E to the u becomes e to the u, which is e to the 1 over n. and that is like this. I accidentally wrote 8. Infinity is what I meant. And this negative is outside. So what we'll do now is do the top first. So e to the 1 over t, which is this, which is infinity. Well, there we go. Equals, well, we know 1 over t as t approaches infinity is 0, so this equals 1, because it's e to the 0 is 1. And then we subtract that, so we have 1 minus e to the 1 over 1 is just e. And that's all negative. So we can rewrite that as e minus 1. And e minus 1 is a finite value. And therefore, the series converges. Okay, cool. Now, problem 30 is, oh, it's another alternating series one, which is nice because those are pretty easy. This one involving j, negative 1 to the j times radical j over j plus 5. So we'll solve this the same as we solved all the others. Take the limit as j approaches infinity of the non-alternating part, which is this, radical j over j plus 5, which is just, we can see that the higher power is in the bottom because this is j to the 1 and this is j to the 1/2 or square root of j. That looks like negative 1, that's a j. Okay, so this means that the limit equals 0 and this converges. Okay, cool. Now the final problem, and the trickiest problem, is problem 33. And it goes like this: the sine of 1 over n over the square root of n. So what we'll do here is compare it to 1 over n to the 3/2, which is a p-series, right? Where p equals 3/2. So this converges, this converges. But sine n, or sine of 1 over n, we know that's going to be less than or equal to 1, right? So just looking at the tops, sine of 1 over n less than or equal to 1. But looking at the bottom, the square root of n is also less than, or I guess equal to when n equals 1, or equal to n to the 3/2. So it's unclear whether, it's unclear by direct comparison whether the left expression is greater than or less than the right expression, right? Because if the denominator on the left had been greater than or equal to, then it'd be obvious that the left is less than the right, but it is not. It is less than or equal to, or the denominator is less than or equal to. So therefore, we will go into the limit comparison test. So we'll take the limit as n approaches infinity of the function or the expression that we have, which is sine of 1 over n over radical n, and we'll divide that by the function we are comparing it to, 1 over n to the 3/2. And this equals, we'll convert it into a nicer form by multiplying by the reciprocal. And I'll write this as n to the 1/2 just for this step. because we can see that n to the 1/2, or n to the 3/2 divided by n to the 1/2 is just n equals n to the 3/2 minus 1/2 equals n to the 2/2, or just n to the 1, or n. So we have sine of 1 over n times n over n, which just cancels out 2. Or this is 1, my bad, times 1. And we have the limit as n approaches infinity of this. And so here, let me rewrite this down here. And I put it too close. Oops. Let me move it. There we go. Okay. So this, if we take it like this, sine of 1 over n as n approaches infinity, well, that's just sine of 0, which is, let me think the unit circle. That's also 0. So we're left with 0 times, well, infinity. And this is, we don't know what that is. So we're going to use L'Hopital's rule. Or first, I guess we'll convert this. First, we'll convert this into a form that looks like this: sine of 1 over n to the negative 1. Now we'll do L'Hopital's rule and take the derivative of the top and the bottom. So the derivative of sine to the 1 over n, well, let's see, derivative of sine to the n, cosine 1 over n, but then obviously we have to do the chain rule. So the derivative of 1 over n, or n to the negative 1, is negative 1 over n squared. So let me just do that. And the derivative of n to the negative 1, again, negative 1 to the n squared. So this cancels with that, and we're left with the limit as n approaches infinity of the cosine of 1 over n, which is the cosine of 0, which is 1. So since 1 is between 0 and infinity, we know that the top and the bottom have the same behavior. And so since the bottom we know converges, then the top also converges. So this series converges.